Hey guys, so in this video we're going to be discussing how we can graph the integrated rate laws. So integrated rate laws are actually a way in which we can determine the relationship between concentration of your reactant versus the time of the reaction. So remember, the common form of a rate law is that rate is equal to K, which is the rate constant, times our concentration of reactant to the n, which represents the order of that reaction. And so through calculus we can actually derive these integrated rate laws, which we will be discussing. And these integrated rate laws allow us to plot linear relationships, because these integrated rate law expressions are actually in the form of y equals mx plus b. So the rate laws for a zero first and second order reaction are shown here, the integrated rate law. And so we can see that for a zero order reaction, we have that the concentration of the reactant at a certain time of the reaction is equal to the negative rate constant times time plus the initial reactant concentration. Now if we compare these factors to y equals mx plus b, we can see that x is going to be analogous to t, and that's actually going to be true for all of our different order reactions. So always on the x-axis we will have time. In the case of our zero order reaction, our y is going to be equal to the concentration of our reactant at a certain time. So we can see that those two are analogous in the equation. Our slope for zero order is equal to the negative rate constant, and our y-intercept b is equivalent to the initial reactant concentration. Now moving on to the first order integrated rate law, we can see that the difference between zero and first is that the concentration of our reactant is actually now the natural logarithm of our concentration at a time and the natural logarithm of our initial reactant. So what changes here on this graph is that our y value, our dependent variable, is actually the natural logarithm of our reactant concentration. And so you might have to actually manipulate the concentration values of the reactant and take the natural logarithm in order to plot x versus y for a first order reaction. Our slope in this case is still the opposite of the rate constant, so the negative rate constant, and in this case our y-intercept is the natural logarithm of the initial reactant concentration. Now our second order reaction has the integrated rate law of 1 over the concentration of our reactant at a certain time is equal to K times T, so the rate constant times the time, plus 1 over the initial concentration. So we can see that x is still the variable time. Our dependent variable y in this case is the inverse of our reactant concentration. Our slope that we would get from graphing x versus y is going to be positive k, so note the difference here that this slope is going to be positive, and our y-intercept is going to be the inverse of our initial reactant concentration. And so it is common that chemists who will have data about the reactant concentration at a certain time of a reaction will actually plot these different zero, first, and second order plots in order to determine the rate of that reaction with respect to that reactant. So let's actually take a look at these plots in a little more detail. So for a zero order graph, remember, here's our integrated rate law. It's the concentration of our reactant at a specific time is equal to the negative rate constant times time of the reaction plus the initial reactant concentration. And so if we recall that this is actually going to be analogous to y equals mx plus b, we can plot time on the x-axis, the concentration of the reactant at that time on the y-axis, and ultimately end up with a line that has a negative slope. And remember, the slope of the line is analogous to the negative rate constant, and so that's why the slope of this line is negative. And here at the y-intercept of the line, we have the initial concentration of the reactant when the reaction started. So looking at a first order plot for a first order reaction, remember that our integrated rate law here is that the natural log of the concentration at a time is equal to the negative rate constant times time plus the natural log of the initial reactant concentration. And so again, this plot is going to be analogous to y equals mx plus b. So by graphing time versus the natural logarithm of the concentration of the reactant, we should again get a linear relationship. So we'll have a line that has a negative slope, and this slope is going to be equal to the negative rate constant. And in this case, our y-intercept is going to be equal to the natural logarithm of the initial concentration of the reactant. So for example, if you were given the equation of the line for a first order plot and you were given the y-intercept, and say that the problem wanted you to solve for just the initial concentration of your reactant, then you would actually have to take the intercept is equal to the natural log of your initial concentration. And to solve for just this initial concentration, you're actually going to need to raise both sides to the e, because e is the opposite of ln. And so ultimately those cancel out, and you get that the initial reactant concentration is equal to e to the y-intercept. And finally, if we take a look at the second order graph, we can see that 1 over the reactant concentration at a time is equal to the rate constant times the time of the reaction plus 1 over the initial concentration of that reactant. Again, this expression is analogous to y equals mx plus b. And so by plotting time versus 1 over the reactant concentration, we should yield a linear relationship. And so this line is actually going to have a slope which is equal to k. And so remember that this is different from our 0 and first order plots, because those had a negative k equal to the slope, where second order is the only plot which has the slope equal to the positive rate constant. And additionally, our y-intercept is going to be equal to 1 over the initial reactant concentration. And so similarly, if we were given the equation for the line for a second order plot, and we were asked to find the initial concentration of the reactant, we would say that the y-intercept b, so that actual value, is equal to 1 over the initial reactant concentration. And in order to solve for just this value, we would need to multiply by this initial reactant concentration on both sides. And so we can see that these two variables cancel in this case. And then to solve just for the initial reactant concentration, we would divide by b. So ultimately the concentration of the reactant initially is going to be equal to 1 over the y-intercept. So in summary, if we plot time versus reactant concentration and yield a linear relationship, we know that this was a 0 order reaction. If we plot time versus the natural logarithm of the reactant concentration and yield a linear relationship, we know that the reaction order was first order. And if we plot time versus 1 over the reactant concentration and yield a linear relationship, we know that that reactant was a second order reaction.